Gross. I am a staff program director with IEEE Future Directions, and it is my pleasure to welcome you this morning to our second week of the 2025 IEEE Online Forum on Climate Change Technologies. Throughout this week, we will have 11 more presentations. Thank you for joining us this morning. I'd like to simply remind you as we go through our presentation to mute your line if you're not speaking and to turn off your videos if you're not presenting. The copies of this presentation will not be shared, but it will be posted for online viewing. So we will invite you to check our website and to access the on-demand recording for this session. While you're listening to our presentation, I also encourage you to submit your questions and your comments on the chat function of this Zoom meeting. We will be moderating a question and answer session at the conclusion of the presentation. The entire presentation will last approximately 1 hour. So now I'd like to introduce our speakers. This morning we have a two-speaker team doing our presentation. This is Tariq Samad and Pramod Khargonekar. Pramod is from the University of California at Irvine, and Tariq is from the University of Minnesota. They will introduce themselves briefly to you when they start their presentation. The title of their presentation is Controls Technology for Climate Change Mitigation, Adaptation, and Resilience. It is with great pleasure that I now let my presenters start their presentation. Thank you.
Thank you very much, Kathy. It's a pleasure for Pramod and me to discuss the role of control systems in addressing various aspects of the climate change challenge facing humanity and the planet. Over the last few years, we have led an effort on behalf of IEEE Control Systems Society on this topic. This included organizing a related session at the IEEE Clean Tech Summit in Glasgow last month. And our thanks to Charlie Jackson for attending the session and for the subsequent invitation for this presentation. So by way of introduction for myself, I'm at the University of Minnesota, as was already stated, where I hold a chair in the management of technology in an organization called the Technological Leadership Institute. But my background is primarily on the industry side. I was with Honeywell International for 30 years, retiring as corporate fellow before coming to academia. I'll be doing the first part of this presentation, and I'll let Pramod introduce himself when he takes over after a few slides. So we would like to talk to you about why control systems are a critical enabling technology for climate change mitigation, adaptation, and resilience. We'll include many examples and details over the course of our presentation, illustrating the strong connections between the discipline that we are coming from and the urgent societal need. So Pramod, if you could move on to the next slide. So let me start by motivating this connection. And the fundamental basis for this presentation, for this effort that we've been undertaking, is that Earth is a complex dynamical system. That means it is large scale, it evolves over time with nonlinear and hybrid characteristics. There are vast uncertainties associated with its evolution, and multiple timescales from the short to the long means decades or longer, are involved. So we have to have an understanding of dynamical systems if we are to have any hope of addressing climate change effects. And on the next slide, this is an animation, you'll see a diagram, and of course you'll recognize it as a control system diagram. Many of you are likely familiar with this pattern, if we can call it that, in the context of engineering systems, be it power plants, aircraft, automobiles, biomedical devices, buildings, or many others. But the concept and picture are equally relevant as we consider how we can manage other systems that go beyond the engineering realm. So in fact, at its core, control is a rigorous approach for effectively managing complex dynamical systems. This means that it provides tools and methodologies for how we can efficiently, reliably, and safely cause complex dynamical systems to behave in desired ways. And that is in spite of all the uncertainties they exhibit and the disturbances to which they are subject and all the other effects and complications that arise from from their complexity and their complex dynamics. So hence the relevance to climate change mitigation, adaptation, and resilience. Here we are looking at closing the loop around the planetary scale climate system, as well as the innumerable smaller scale dynamical systems of which the former is composed, and the innumerable smaller scale dynamical systems, many of which are in fact human engineered, that influence climate change phenomena. The actions we take, and in fact, one might argue that now our inactions, will help determine whether we end up with a livable, sustainable planet or not. On the next slide, we just go one level deeper and list some of the key areas of expertise within the controls discipline that are so central to this whole challenge of addressing climate change. First, in order to manage and control dynamical systems, we must be able to model them. So much of control engineering is dedicated to modeling dynamical systems. And that's even in cases where our knowledge is incomplete, the data is available is inadequate and uncertain, measurements are hard to come by, and all these other complications. Feedback is, of course, closely associated with control systems and sometimes is viewed as synonymous with control, although control is much more than feedback. Closing the loop around a dynamical system, if done well, can ensure it behaves the way we want it to. But on the other hand, if done poorly, feedback can lead to instability and other bad outcomes. The tools that controls researchers have developed for feedback control, again under uncertainty, limited measurements, and complex dynamics, are in fact essential to our civilization today. We use feedback and feed-forward strategies to get systems to behave optimally, subject to our criteria and objectives and subject to various constraints. So optimization is another key element. Another critical feature of a dynamical system is that it has state. There are internal variables that influence the evolution of the system that may not be readily measurable. These states must be estimated in order to manage and control a dynamical system. State estimation is thus another essential part of the control engineer's toolbox. Control engineers also typically have to deal with human-in-the-loop considerations in designing, implementing, and operating control systems, whether it's in the context of aircraft or automobiles or power systems, and in non-technical systems, non-engineered systems as well. And these considerations are especially relevant in the current context of climate change. Let's move on to the next slide now. So that was all by way of motivational background. And let me just switch gears now for a bit. A few years ago, Control Systems Society, under the leadership of then President Anuradha Anaswamy, launched an initiative to develop a Roadmap 2030, quote unquote, vision for the field. Pramod and I were asked to lead one facet of this on climate change. We worked with a number of experts in our community in this process, and one outcome is an article published in Control Systems magazine last year titled Climate Change Mitigation, Adaptation, and Resilience, Challenges and Opportunities for the Control Systems Community. The first page of the article is shown here. It's available on Explorer, as you might imagine, and the QR code will get you directly there. We like to think of this article as a comprehensive and expansive view, perhaps the first one in the field of the topic. The article starts by reviewing recent information on the impacts of climate change, projections for their worsening, and high-level analyses on how greenhouse gas emissions could be sufficiently reduced to avert catastrophic outcomes. We rely on sources such as the IPCC reports and the IEA and others in this part. We also discussed the importance of addressing adaptation and resilience in addition to mitigation. The boat has, to some extent, left the shores today. It's impossible now to think of a world which is unaffected by climate change. So adapting to climate change and being resilient to future effects of climate change are going to be just as important as reducing greenhouse gas emissions. The core of the article then is titled Targets of Opportunity. In this part, we outline 14 areas where significant opportunities exist for control scientists and engineers. These areas are listed on the slide. And as you can see, they include not only topics like electricity generation, transportation, buildings, and industry, which are often discussed in the emissions context, but also information and communication technologies, alternative fuels, food and agriculture, water, and beyond. A couple of the areas, notably infrastructures and socio-technical systems, suggest opportunities that are more aligned with adaptation and resilience than mitigation. Pramod will be discussing a few of these targets of opportunity in more detail coming up. The article also makes the point that climate change mitigation and adaptation are complex and not just engineering or technology problems. So broader perspectives must be kept in mind by researchers as well as practitioners. We discussed in this context the need for sustainable economic growth, for facilitating the progression from undertaking the research to large-scale deployment, to enhancing education and awareness, the need for equity and social justice, the requirement for transdisciplinary collaborations. And again, Pramod will say a few more words about these. On the next slide, you'll see it's a pretty dense slide. It's actually a table from this article. And what we do here is that for each of these 14 targets of opportunity, we include, first of all, a brief discussion of each target, 2 or 3 paragraphs in each case. And then we follow these with example opportunities, more or less specific opportunities in each of these targets. So we identify also whether these opportunities are in the short term, the medium term, or the long term. This slide tabulates this whole set of example opportunities. They are categorized, as you can see, as short term, medium term, and long term. And there's also color coding associated with the bullets. And the legend at the bottom right shows the opportunity area associated with each example through the colors. So to call out a few, under short-term opportunities, and by the way, I should say that we define short-term as meaning that societal scale impact can happen by the end of this current decade, by 2030. So in this short-term, we can see there are a number of topics here, but they include power electronics for renewable sources, energy management for data centers, and irrigation and land use in agriculture. Then in the medium-term timescale, and that means societal impact during the decade from 2030 to 2040, we list opportunities such as floating offshore wind, tidal and wave generation, net zero, net positive smart cities, and energy justice in generation and distribution. And then in the long-term horizon, with societal impact post-2040, we include resilient coastal structures for rising sea levels, artificial photosynthesis, and policy and infrastructure design. The importance of incorporating policy considerations is, in fact, something we highlight in multiple places in the article. You'll note that we don't explicitly call out control systems in these examples. We have deliberately foregrounded the application areas rather than the technological or the control theoretic underpinnings. But this slide really shows just the huge variety, diversity of space of critical problems related to climate change, mitigation, adaptation, resilience, in which control technology has a crucial role to play. So it's now my privilege to welcome Pramod Khargonekar from the University of California, Irvine to the virtual podium. Pramod will delve deeper into some of these areas and discuss other aspects of control for climate change as well. Pramod, over to you. Thank you.
Thank you, Tariq, and good day, everybody. Before I sort of launch into the next set of slides, let me just say that Tariq and I were really fortunate to be asked to co-lead this effort on behalf of the entire Control Systems Society to look back and see what Control Systems has already done, what Control Systems colleagues have already done in various facets of climate change mitigation, adaptation, and resilience, and also to look forward. And Tariq just gave you kind of a glimpse of that article that appeared in Control Systems magazine. And I certainly, we don't have the time, nor would it be appropriate to go over everything that we wrote in that article. We certainly recommend that you take a look at it on IEEE Explore, and Tariq shared the link to it. Let me make a couple more points before I sort of launch into my part. One is we wrote the article, we did this work from say something like 2022 to 2024. Part of it was during COVID. And of course, the geopolitical climate situation was, I think, quite substantially different than it is today. And so what we are going to say really, is based on the work that was done roughly 2, 3 years ago. And the world situation is not quite the same as it was. On the other hand, as I will explain, a lot of the things are still very much applicable and a lot of the thinking is still very much valid. It's just that in 2025 reality, one would have to account for the change to achieve success. So, we are just coming off of COP30, and I'll make some comments on COP30 and what's going on in due course. But I think it's really important to recognize that we live in a somewhat different world situation than we did when we did the paper. So there are a few trends that I think are really ongoing and question are still valid and very much relevant. And number one, I would say, is just the fact that global energy consumption continues to increase. And it's largely driven by uh, billions of people coming out of poverty and achieving middle class and higher living standards, across Asia, Latin America, Africa, and other parts of the world. And so there is no question that to enable, 8.5 billion people to live a reasonable standard of living, we will be needing more and more energy. Even in the developed country like United States, we are seeing energy consumption increase. So I think that's the number one factor, is that this we cannot wish away the need for increased amounts of energy. A positive sign is falling prices of carbon-free electricity. So solar PV as well as wind, solar PV more spectacularly than wind, but both of these technologies have really driven down the cost of electricity production, and it's carbon-free. So without any sort of subsidies or social policy, economically, one can say that in many parts of the world, solar and wind are economically competitive sources for electricity. And I think that is a big positive factor in this whole climate change situation, is that here are two technologies that are really can drive a lot of progress. Another factor that I think is becoming more and more compelling is falling prices of battery storage. They really have come down dramatically, and they're on track to go down even further in the coming years. And when you combine these two facts, suddenly you get a vector for change that is very significant, regardless of other considerations. Fourth point we will make is energy efficiency still remains the lowest hanging fruit. So if you combine my point that we need more energy, well, we can reduce that growth curve quite substantially, as a matter of fact, by paying attention to energy efficiency. And although we won't have, we won't call out our paper with respect to energy efficiency, control systems play a huge role in energy efficiency in buildings, in manufacturing, in transportation, and in many other places. So it's like really a sweet spot for controls technologies to reduce the energy consumption in existing areas. And then finally, mitigation is not enough. Adaptation and resilience are urgently needed. And I think that realization has been dawning for some time, but I think now it is incontrovertible. I was just, I didn't mention this, but actually I'm not speaking from California. I'm right now in India. And news here is full of the devastating storms in Southeast Asia. I think something like 950 people have died. Maybe my number is a little bit off, but it's in triple digits, the number of people who have died by these storms. And in fact, it's not just a single storm. There is a collection of storms that have come together to cause this devastation. So we have gone from a single hazard to multi-hazard coming together to affect human civilization. And I think that's calling for much greater emphasis on adaptation and resilience. So we will say something about that. Here is just like a snapshot of control and clean tech solutions that are here and now. And I think people are working on these and they are very viable and are going into the real world. So for example, and again, I'll amplify on these, but this is in a single slide. Control and optimization of renewable electricity production. So electricity and making it clean, fossil-free is the most viable path for reducing GHG emissions right now. Other areas are harder. This is, in many ways, it's here and now, and control can play and does play a very big role in optimizing how much electricity we can produce from things like solar PV and wind farms. And I'll show you an example in a couple of minutes as to very advanced control technology that's being used for optimizing energy production, reducing cost further. Second area, as we put more and more renewable electricity on the grid, managing the grid becomes a big challenge. These sources are stochastic, they are not controllable. Of course, you can put some battery storage to improve, but nevertheless, at the end of the day, dealing with the stochastic sources of electricity production is a major engineering and technological challenge, and control plays a very big role in solving that problem so that our grid is reliable, it's economic, and is sustainable. So that's another area. Third area where I think control is having a big positive contribution is energy storage. I talked about how battery prices are going down. And so batteries everywhere from EVs to grid scale storage to distribution side batteries in many, many different parts. Um, Optimizing the use of energy storage through control and optimization techniques is a very big opportunity for control technologies to make a contribution. Uh, in the transport sector, really the most compelling vector for change right now is electric vehicles, which have really done remarkably well in many parts of the world, and China is making amazing contributions to electrification of passenger vehicles. And then that leads to a whole bunch of control technology opportunities in charging of the electric vehicles and managing the grid, because then it sort of connects the electricity system with the transportation system. I spoke about energy and resource efficiency in buildings, transportation, and agriculture, a huge opportunity. And then finally, data-driven control and decision-making for climate resilience to extreme events. So let's talk a little bit about some of these things. So electric power generation, it's an urgent priority to decarbonize fossil fuel-based electricity production. As you know, coal used to be the dominant or one of the dominant sources of fuel for producing electricity. Then natural gas has made a big contribution. Of course, there is traditional sources like hydro, which is clean, and nuclear, which is carbon-free. But rest of it comes from fossil fuels. So the change that can be made here in mitigation is to replace coal and gas with renewable like solar and wind. But this ramp down in fossil fuels will not be instantaneous. It's going to take many, many years, and they will continue to be used for a few decades to come, especially when you consider that economies are growing, people's living standards are going up. So this is a major challenge to go from here to a fossil fuel-free electricity system. Cost reductions in solar and wind have been dramatic. Cost parity or better with fossil fuels in many locations now. And then there are other green energy options that are promising where controls plays a role. And here are a couple of examples. Geothermal is a big opportunity. It's underexploited resource. It is not stochastic, so if we do it right, this is one of the more controllable sources of electricity. And marine and riverine hydropower are other opportunities that have not been fully exploited. So those are carbon free. And then, we absolutely have to put nuclear on the table. So small modular reactors, lot of progress there, and fusion, which is out on the horizon. And both of these technologies have a lot of control opportunities, and control technology is playing and will play major role in rollout of nuclear. So that's what the last bullet says, that in all of these things that I mentioned, control plays a major role. And so here are some examples that in our paper we mentioned. dynamic management and optimization of large-scale renewable energy generators. So we want you to think here of, say, big wind farms or big solar farms. So you've got a large area covered with these wind and solar. How do you optimize their dynamics together to maximize the energy output? And a lot of control systems colleagues work on these types of problems and increase the total energy production, electricity production. Second bullet, let me wait till the next slide because I'm actually going to show you what some of control colleagues are doing in floating offshore wind. And then finally, this is a little bit longer term. For the long term, when we get high levels of renewable generation on the grid, we will have issues of seasonal storage. That is, the production in winter is not the same as production in the summer and spring. So you're going to need to be able to store electric energy on almost like a month or a couple of months basis. And that's more or less an unsolved problem. And their hydrogen and biofuels and some other technologies could play a role. So that goes under heading of seasonal storage or that sort of opportunity. And I think that's a long-term need that still needs to be met. Here is an example from our colleague Lucy Pao at University of Colorado Boulder, and it's on floating offshore wind turbines. So for floating offshore wind is not as mature as onshore wind turbines that we see in say in California or other parts of the world. Offshore is still more expensive, and one of the factors that increases cost is platform. So platform amounts to more than 20% of a floating offshore wind turbine. And so if we can reduce the platform weight, then we can reduce the cost. But as we reduce the platform weight, the dynamics and stability of the floating offshore wind becomes a major problem. So here is an example that Lucy has provided where they are doing simulations of an offshore wind turbine with this lightweight platform. And as the wind changes, the whole tower shows dynamics, and then the platform has to keep it all stable. So it's a sort of major multivariable control systems problems. And Lucy's work has shown that suitable design of control system can make these things viable, stable, and produce electricity, at the same time reduce cost. So we think this is a nice example of where leading edge control is making a contribution. I had mentioned that as we increase the amount of renewable electricity on the grid, grid management becomes a big problem. And the way to think about that grid management problem is through what is called flexibility. So flexibility is defined as the capability of a power system to cope with variability and uncertainty that renewable generation, VRE stands for variable renewable electricity generation, that introduces into the system in different time scales, from very short to the long term. In fact, all the way, like I was saying, to seasonal, multi-month. And so this variability is something that you have to deal with. And the way to deal with it is by flexibility. That is, as the renewable portion goes up and down, other pieces in the grid have to absorb that stochasticity and keep the system stable. So it's a major problem. And here is a paper from 2015 from NREL that shows many different techniques that can be used for solving this problem. And they range from operating the system in a more clever way to markets, load flexibility, flexible generation, managing the electric network both on the transmission and distribution side, as well as storage, thermal storage, pumped hydro, and chemical. So these are all different techniques. They all have different costs. So the problem becomes, what's the most cost-effective way of managing the grid to manage the stochasticity of the renewable generation? So this is the 2019 chart from IRENA that shows what are the enabling technologies, and you can see utility scale batteries, behind the meter batteries, electric vehicle smart charging, renewable power to heat. Then you have some innovations in business models, you have market design, increasing time granularity in electricity. I don't have time to tell you about electricity markets, but that's a big area where people from controls background make contributions. Space granularity here, what we mean is distribution of renewables across the grid and so forth. So these are all enabling technologies and research opportunities for deep renewable integration. And in almost every one of them, controls plays a significant role. So here is a chart that we talk about in our paper is what can learning and control do for enabling deep renewable integration. So learning and control for management of distributed power systems. This is where control really shines. So imagine you got these renewable generators, you got electric vehicles, millions of points that need to be managed to minimize the impact of randomness. And distributed control plays a huge role in solving that kind of a problem. Forecasting plays a big role. So if you can do a forecast better of, say, solar or wind, the control problem becomes that easier. Sub-hourly dispatch, this is a market thing that control techniques can help optimize. Larger balancing areas, market design. Ramping is a big problem. So as sun goes down in the afternoon, the solar production goes from, say, peak to zero in maybe an hour, and that produces a huge ramp down in solar output. So somebody else some other source has to take up that slack. And so what do you do to deal with that is a major issue. And again, control plays a major role in solving that problem. Dynamic control and optimization of energy storage, both on the grid scale as well as distributed storage across the distribution system. Demand side management, we can get a lot from harnessing the inherent flexibility on the demand side. Think your water heater or pool pump. I mean, these are flexible loads. And again, distributed control of these millions of these types of loads gives you enormous capacity to make the grid green. And distributed energy resources, rooftop solar, electric vehicles, microgrids. Now, moving on from electricity to transportation. Transportation is about 15% of global GHG emissions. It's very big. IEA's goal for net zero is to reduce the oil to 10%, which is a really, really major challenge. And I think what we are seeing is electric vehicles as the game-changing solution. And their costs are coming down and their range is going up and so on and so forth. So what that does is it creates a whole new set of opportunities for controls. So how do you charge all these fleets of vehicles across the grid? And so distributed optimal algorithms for large-scale EV charging. Then there is all the vehicle to grid and vehicle to everything integration. So these electric vehicles and batteries can become a resource to the grid. And so how do you manage vehicle to grid energy transfer? And human in the loop is very important because it's people's behavior when it comes to use of electric vehicles and charging that's going to play a very big role. Decarbonization of air and marine transport is not as advanced, but there are control opportunities beyond electrification, for example, in hydrogen, ammonia, sustainable fuels. And then finally, all of this is a system of systems. So if you think about the total transportation system, which is cars, airplanes, and bicycles, and so on and so forth, there is a whole network of systems, and especially for logistics and freight, can be optimized. So here are some opportunities that we highlight in our paper for the transportation sector. Moving on, industry and manufacturing is the biggest GHG emitter. About 34% come from power and heating in industry. This is actually a very, very hard problem. There is tremendous diversity of industrial facilities and processes, and detailed processes knowledge is required, and opportunities can be sector specific. And there are some GHG sectors that are very hard to electrify, although a lot of really good people are working on this. So for example, cement and steel and some others are really hard. And there are many approaches. Circular economy is one approach. There are inherent feedback loops in all of these things where control can play a role. Electrification of some of these things, and then making electricity renewable is another major vector for this. So, this area is rife for control because these are all processes. And so if you can do process control and optimization, reduce energy use, make it more efficient, use renewable sources of energy, these are all things that colleagues in our community work on. Control co-design for greenfield net zero projects. So if things that are being built new, control can be brought in at the design stage and leverage Industry 4.0 type of enablers to reduce, if not eliminate, GHG emissions. And then what do you do with, say, stored CO2 and so forth? And so what kind of utilization can be made of those captured gases is a long-term opportunity where we think process design, control, and optimization can play a role. Homes, buildings, and facilities is about 16 to 17% of GHG emissions. This is an area where control is natural. So think of your HVAC system either in your office building or at home. How do you make it as efficient as possible? Is a natural control question. And sensing of occupancy and so forth. A lot of good work in control is being done to improve HVAC energy efficiency. And then interestingly, and again, this work has been done and is continuing, buildings and homes can also become flexible loads for renewable integration. So how do you turn these into controllable loads, flexible loads, so that you can match what renewables are producing? Microgrids is another option where again control plays a major role in managing these microgrids. And then heat pumps powered by renewables is a key technology vector to make homes, buildings, and facilities less GHG intensive. And here are some example technologies that we mentioned in our paper. I want to move now to adaptation and resilience. As I mentioned earlier, mitigation is necessary and important, but we can't wait. So we have to adapt and be resilient. This chart just shows you how to think about adaptation and resilience. So it's a mix of three factors. It's the hazard. So think here hurricanes or storms or wildfires. And then there is vulnerability. So populations or facilities or areas that are vulnerable to that. So homes near wildfires would be vulnerable to wildfire. And then exposure. So things along the coast or houses near wildfire zones would be exposed to that risk. So if you can reduce exposure, reduce vulnerability, and reduce hazard, then you can reduce. But then there is a limit to how much you can do by reducing all these three factors. And so for that, you have to somehow think about what are we going to do to become more adapted and resilient. And here the main point we want to make is that adaptation and resilience versus mitigation can be synergistic or can have a trade-off. So there are some examples where, for example, for mitigation, you might want to increase amount of hydropower. Well, it's a good idea, except if it's done in hazard-prone areas where you could have storms or a drought situation, that can actually make things worse. So mitigation action can increase exposure to vulnerability to climate change. So that's an example of a trade-off. Another example of a trade-off is for public health or for keeping people cool. And I'm absolutely sensitive and empathetic to the need for air conditioning in hot areas. I'm in India right now, and really you need the air conditioning. But then it undermines mitigation efforts. So on the other hand, this is an example above is to reduce climate change impacts, you can increase urban green spaces. So for reducing urban heat island effects for heat waves. So you have urban green spaces that keep things cool, but they also help with GHG reduction. So when you think about adaptation and resilience and mitigation, one should be thinking about how they can be made more synergistic And so distributed energy systems can enable greater renewable integration as well as resilience. Resource optimization in agriculture can be better adapted to future arid climate and higher temperatures. And electrification of transport can give you better public health outcomes. So controls technologies for adaptation and resilience. Key tools in this area are forecasting. Number one, if you can do forecasting of these hazards, you can take appropriate adaptation, resilient action. Planning before the extreme event, stochastic dynamic optimization, again, a key technology that control people are experts in, and decision and control. So as example, resilience needs against extreme events such as wildfires, hurricanes, storms, and heat waves. And the key goal here is to minimize disruption and recovery time for critical infrastructure such as power grids. So one of the worst thing that can happen is you get hit by one of these extreme events like a wildfire or a hurricane and you lose electricity. I mean, that's life hazard. People lose life over something like that. So if you can reduce the amount of time that the grid goes down and you can bring it back up, or the transportation system or the communication system can have a huge impact in terms of resilience of that community or of that area. Critical health and life support services for responding to heat waves. We have heat waves almost every year. People lose their lives. What can we do in terms of forecasting, planning, and optimization? And then in longer term, we think that resource optimization for agriculture and food is going to be absolutely critical. And again, control technologies can play a role in that. To wrap the presentation up, we are focused mostly on power and energy system because that's what we know well, and that's where our technologies have the biggest impact. But we recognize that these are subsets of the economic system. So, we should be working on these things, but we need to be thinking about jobs for people and making sure that we are living within planetary boundaries, etc. And then the economic system is inside a social system. And we have to think about inequalities and fairness and justice and so forth, and social participation. And finally, this is all within the Earth system where we humans live along with other life forms. And just to make everything, for example, biodiversity is a huge imperative. So we have to be mindful of this larger picture as we think about technologies. In our paper, we highlight a few facts. Number one, none of this is a pure controls problem. So we have to have multidisciplinary collaborations to have any chance of success. Cost effectiveness and scalability is absolutely crucial. If it's not cost effective or scalable, it's not going to work. Infrastructures last for decades. And so how do you make decisions under deep uncertainty? Research should connect with innovation and deployment. We have to go beyond engineering and technology. Social and economic justice should be central in our thinking. And most importantly, is students are very interested in working on these issues. So that gives me a lot of hope for the future. I'm going to turn it over to Tariq for the final words, and then we will open it for questions. Tariq?
Yes, thank you. Thank you, Pramod. So we hope you get a sense of the wealth, depth, and breadth of opportunities for control systems. We might also say that there's an equally substantial burden of responsibility on our community as well to help the world deal with climate change. We thought we would end by reflecting on the process we went through and some of the lessons we learned. As Pramod mentioned, this took about 3 years. Overall, we involved perhaps 40 people from around the world. There was an in-person workshop in Stockholm and multiple Zoom sessions and many other discussions as well. Perhaps the first point to make is that we were asked to lead this effort because of our background in the area and a long history with Control Systems Society and the controls community. Looking back, perhaps some younger blood would probably have been a good addition too. It's important to remember that the next generation has so much more to offer going forward, and in fact, so much more at stake as well. We were, however, able to get many future leaders involved in the effort. The importance of looking at broader perspectives in something of this much importance is essential. So we would argue that limiting the scope solely to research needs would be quite short-sighted. We also had some discussion about how we should organize the output that we were producing? Should it be under technology topics, control technology topics, such as modeling and identification, control design, feedback, estimation, optimization, etc., or more on the application space? And we opted for the latter, and in part because we really wanted to produce something that was understandable and of value beyond the controls community. So the targets of opportunity we highlight are in fact industry or economic sectors. A challenge was insisting that we identify some time horizons for societal impact. This was quite a challenge because researchers tend not to think in terms of, okay, we are here now and further research needs to happen, but at some point we want to have an impact on society at large scale, and how long will that take? It's a hard thing to be able to estimate that, of course. But I think if we want to have a mindset of R&D for the sake of societal impact rather than research for research sake, we have to have some put ourselves through this challenge of identifying what timing would be involved. There's some more examples learned as well, addressing the need for engaging the right experts that cover both theory and application, keeping in mind that this is our ultimate goal is really motivation and communications, and so outputs should be developed appropriately for those goals, and that follow through with different target audiences should be maintained. And I should add that we particularly focused on 3 customer segments in mind, kept those in mind. One is young researchers, because as we said, they are the ones who are truly we're going to be handing on the baton and all the problems for that matter too. Secondly, professional organizations such as IEEE and in particular Control Systems Society. And thirdly, funding agencies. So as I said, if any of you are considering a similar undertaking under your part of the IEEE umbrella, perhaps some of these insights from our experience will be useful to you. So with that, Pramod and I thank you for your attention, and I hope we have some time left for your comments, your ideas, and your questions. And I see that there have been a bunch of good comments on the chat as well, and I don't think I've gone through all of them, but I was trying to respond as Pramod was talking.
Thank you.
Yes, exactly. Thank you so much, Tariq and Pramod, for this really comprehensive overview that gave us a really good sense of how control systems our technologies are sprinkled throughout this problem of climate change. So thank you. We did indeed have a couple of questions that came into the chat during your presentations. And Tariq, thank you for keeping an eye on this and writing some answers already. But for the benefit of our viewers who will be looking at our replay, I'd like to go back through some of these questions. So, Pramod, you mentioned on one of your charts the concept of circular economy. We had a couple of questions that related to this concept. The first one was about control technologies that may address waste production and its consequences, which are on both sides of the circular economy flow, one on the side of resource scarcity and the other one on the side of pollution. And as an addendum to this question, there was another one that asked, well, what specific sector would be the greatest challenge for addressing both perhaps the side of energy consumption and greenhouse gas emission reduction? So that's another question related to that circular concept. So do you have more comments on that?
I don't know. Did Tariq already address this? Because I can.
I put some comments down, Pramod, which you can see on the. But why don't you give your perspective as well?
I think without seeing Tariq's response, which is actually a good thing because then he is independent. I think in the circular economy space, the role for control is through process optimization, process control, process optimization. So as we think about recycling and all of those types of things to make the resources circular and not go to waste, they will involve many different processes. I mean, you can just take example of recycling. There are a whole bunch of processes that go in sorting and this and that, and sensing control, process modeling and optimization and control, I think would be the natural opportunity in the area of circular economy. And I think it depends on, like, in plastics, it will be different. In glass and steel, it's going to be different. So there is no universal answer I can give other than to say the key tools of process modeling, process optimization, process control, process sensing, these are all techniques by which control community can engage in circular economy.
Just to sort of reiterate some of what I said, which is quite well aligned with what Pramod just said, I identified some specific areas too. So, for example, control of wastewater treatment systems, if you're specifically looking at waste systems, and emissions control, which is done through process automation and control in industry as well as in transportation. This question about which is the one specific manufacturing or processing sector which presents the greatest challenge, I think that's an interesting question. We were not trying to quantify things at that level to be able to say, okay, which is the one greatest sector. But again, certainly process control and automation, for example, for even today and for the foreseeable future, for control and natural gas power plants, that's not going away. And there has been a lot of work in control and optimization for those systems. Similarly, in automotive and other transportation systems and industrial processes such as oil refining, cement manufacturing, and others. So all of these present a lot of opportunity space for controls.
I think cement and steel are widely recognized as some of the hardest problems that we don't have really good solutions for. People are working. It's not that people are not working on them, but to make them cost effective is a huge challenge.
Yeah, especially like electrification of cement is actually because of the high temperatures involved. It's
high temperature.
So straightforward.
High temperature. Other questions,
Right.
Carol?
Yeah, so the next question on the topic of adaptation and resilience. What area do you recommend most for research? Where do we need the most research?
Okay, that probably is not the same as where I think we are positioned to make a contribution. And I think where we are positioned to make a contribution is planning and responding to extreme events, because that is a dynamic problem. Sometimes we get 5-day advance warning, but it's not perfect, right? Hurricanes change their track. So that area, to me, how do you manage extreme events? Planning for extreme events, responding to them, rebuilding, and then making sure that next time we do it better, faster, less downtime. I think to me is a big opportunity in the adaptation and resilience area for the kind of people that we work with. Of course, it's not a control problem. It's a multidisciplinary problem, but I think that's definitely something to work on. The other thing that I showed as long term, I feel that agriculture and food production for a changing climate has got to be extremely high on list of problems to work on. And I think, with advances in biotechnology and just bringing to bear like the latest and greatest in terms of agriculture and food production, it's going to have a huge impact. And I have a sneaky, although I haven't done like systematic study, I have a feeling that we are not doing enough of this. And climate change is coming. I mean, it's here, it's coming. And I think you're going to get millions of people affected by through agriculture, food. You can add water to it, but I would say, like basic things, basic necessities of life, agriculture, food, water. I mean, I would think adapting to a changing climate for those is absolutely crucial.
Yes, in fact, we are starting a new initiative in Future Directions on that topic called Smart Agri-Food Systems.
Yeah, I know John.
Together,
John Verbencourt, I mean, he's a colleague. I know him from Michigan State. He's very heavily involved. And I certainly, I'm in touch with him, and I'm hoping that controls can contribute to that effort.
Excellent. Yeah. So for all of you listening, if you're interested in this topic, keep an eye on that. So the next question is really interesting. It's kind of elevating the discussion to the planetary scale. It's a long question in the chat, but I'm going to read it to you as it was written. It's very well put. How can control theory be used in the context of Earth systems models, which address many of the multiple feedbacks that you cited related to the atmosphere, land surface, oceans, cryosphere, hydrosphere, biosphere, etc., via an ensemble of solutions of coupled partial differential equations as
Yeah.
an initial boundary problem?
Yeah,
At a
it's
more local scale, as an example, consider how wind and solar power generation is affected by the lower atmospheric boundary layer, and such systems change those weather conditions.
I think that's a great question. Uh, I think as a first cut, including the control action in the loop and actually modeling the loop is already, I don't think, done very well yet. I mean, it's sort of mostly economic modeling that plays a role in how you bring, say, future growth and those types of inputs into the trajectory of, so you have all these pathways and different assumptions on economic growth that you bake into these models. Doing a more sort of control-oriented analysis of proposed actions already would go a long way in terms of making a contribution. And then finding the most effective levers that one can pull to steer this system. I think we have scratched the surface of this. It's a very difficult problem because you can easily sort of lose sight of real world constraints. This our control effectors for this big dynamical system are not very strong, but we have them. Like people's behavior is a big vector. Making the energy system carbon free is a big vector. So kind of beginning to think about that planetary scale, I'm glad somebody asked that question because it is something that has not been done very well. In fact, we have seen some efforts on this, and I feel like more rigorous work along that line is absolutely needed.
Yeah, we have started to see some papers on this topic, actually, relying
Yeah.
on developments in climate science and atmospheric science and these different layers of the atmosphere and their interconnections. Of course, the big challenge is that these systems are really described, as it said here, by sort of these complex distributed parameter systems. And those are not at computationally tractable the way we expect things in control to be. So how do you simplify them to get to the point where you have control relevant models now, not just fundamental phenomenological models, is one challenge. But work is happening in that level, and as Pramod is saying, there are these complex feedback effects as well, because the actions we take influence the evolution of climate, of course.